All right, folks, as previously mentioned, we are starting Chapter 3 today. The first section of Chapter 3 deals with exponential functions. We are not going to focus on the graphing because we are virtual and I don't have a good way to assess the graphing portion. We may come back to it, pick it up later. Instead, we're going to focus on what is an exponential function and how are they used. Okay? So, when we're doing our various math classes throughout high school, from Algebra 1 up through Calculus, there are certain functions that pop up over and over and over again. So here are three functions that we see quite often. This first function, these are your linear functions. We see a ton of those in Algebra 1. Remember that as graphs, they're straight lines, okay? The second one here, that's our quadratics. We see a ton of those in Algebra 1 and Algebra 2. We didn't do as much work with them in pre-calc here, but it is sort of assumed that we know what they look like. Remember that those are your parabolas. And this one is the third one, and it doesn't really start showing up until Algebra 2, and we really take more of a look at what these do here in pre-calculus. These are your exponential functions. And they have a horizontal asymptote. That particular one looks more or less like this. It has a horizontal asymptote at 0, and it will increase exponentially as we move from left to right. The main reason we're talking about this here is because these three families of functions, linears, quadratics, and exponentials, make up the bulk of your SAT and your ACT and SAT questions. So it's very important that we at least get a basic understanding of exponential functions in place here as we move forward. So remember that exponential functions always have a number for a base, a constant, and they have a variable for an exponent. Okay, so instead of having a slope that causes the function value to change, we're actually the variable itself is an exponent, which makes it grow or shrink much faster and never in a straight line. Okay, so we're talking about a lot of real world situations here. I'm going to give you a second here. If anybody needs any more time before I advance, please speak now or forever hold your peace, because we're going to advance down the page. Just grab a quick screenshot of that and throw it into the thing for our completed notes later. Grab that. Still too big. That's more or less what I'm after. There we go. Clipboard, go here and paste. Fix it later. Back to the notes. Okay. So on to the next part of here. We are talking about real world stuff here. Okay. Exponential functions appear all over the place, specifically in population growth, investments. That's how your various interest rates work on your bank accounts. Radioactive decay, probably have seen these in your science classes by now. Same with what we're dealing with right now with COVID. Spread of disease is exponential. If it is exponential, that's a big problem. Remember that flattening the curve thing we tried to do last spring? That was so that it wouldn't grow exponentially fast. And also we're going to have just in general just questions about the basic understanding of exponential functions, which we see on that SAT. So every exponential function comes in the form f of x equals a times b to the x power, where a and b are constants. A is not equal to 0 and b is not equal to 1. Now here's why those matter. If a equals 0, then the entire function equals 0, and that is not interesting, okay? Because if a is 0, 0 times b to the x, here we'll write it over here, equals 0. That's not interesting. That's a straight line. That's not anything that is worth dealing with. So we do not allow a to equal 0. If b is equal to 1, then we have f of x equals a times 1 to the x, which is always a. And that also is not interesting. That's a straight line, not an exponential function. Okay? Because 1 to any power is still 1. So we do not let a equal 0. We do not let b equal 1. The a value is called the initial amount. And b is going to represent our exponential rate. Okay? So a is going to be our initial amount, and b is going to be our exponential rate. Okay, there is a little bit more we have to do with b than what we've talked about, and we'll get to that in a minute when we get to the real life examples. Now, exponential functions come in two types: exponential growth and exponential decay. Exponential growth is when the y values are increasing. And the way we tell that it's exponential growth is the b value is greater than 1. Remember, it's not allowed to equal 1, so only greater than 1. If b is greater than 1, we're looking at an exponential growth problem. Exponential decay is when these functions decrease from left to right. This is caused by a b value between 0 and 1. Okay? Okay? All right. So if b is greater than 1, that is exponential growth. If b is less than 1, it would be decay. B is always a positive number, because if that's a negative number, then we have all sorts of weird things happening with our graph. So B is always positive, and B is never equal to 1. If that value is between 0 and 1, that is exponential decay. If B is greater than 1, that is exponential growth. Grab myself another screenshot here for the completed notes. Go back in. Anybody need more time on this page before we advance? Speak now or forever be annoyed. We're doing okay? It's all still background information. I know it's not super entertaining. All right, Jackson made it back in, so let's get that fixed. Still no Colton. All right. Okay, so on to the next section here. I think we're finally going to get into some stuff where we actually ask questions where I can do something with them. Okay, so example 4 here. Let's talk about growth and decay and how we figure out the horizontal asymptote. Okay, so here we have a function, f of x equals -2 times 3 to the x power plus 5. Okay, so to figure out the growth or decay, we look at the b value. Remember that if b is greater than 1, that is growth. And if b is between 0 and 1, that is decay. So we go in here and we find the b value. Okay, we're going to be locating our b value. It's all about the b. So b is the number that's being raised to the exponent here. Okay, so in that first example on f of x, b is 3. So we have to ask ourselves, is 3 greater than 1? Or is 3 between 0 and 1? Well, 3 is clearly greater than 1. Because 3 is greater than 1, this is exponential growth. Okay? In fact, it is a 300% growth. No, that's not quite right. 200% growth. It's actually 200% growth. Let's get that right. If we're going to do it, let's do it right. Does anybody know where I got 200%?
No.
Okay. So the 3, if it were, okay, 1 is 100%. Yes? So in this case, we have 3, which is 2 bigger than 1. And then that 2, how much bigger it is than 1, is, as a percent, 200%. Okay, we'll look at a few more examples of that because that's going to come up on the Delta math assignment. I want to make sure everybody's clear on that before we finish up today. Okay. As for the horizontal asymptote, we're still going to have the same thing we've seen over and over again throughout our class, y equals k, where that k value is attached right there on the end. Okay, it's attached right there on the end. Okay, so in this case, that k value would tell us that this one has a horizontal asymptote at y equals 5. Y equals 5. All right, let's take a look at g of x there. At g of x. So again, we need to locate the base. So anybody, unmute and tell me what is the base of this second function g of x? What is the b value for g of x? What number is being raised to the exponent?
2/3.
2/3.
2/3. Good. 2/3 is our base. Because 2/3 falls between 0 and 1, this would be an example of exponential decay. Okay. Now, in terms of what percentage decay, 2/3 is less than 2/3 is less than 1 by what amount? How much less than 1 is 2/3?
0.33.
Okay, 3.3 repeating, good. 0.3 repeating, or 1/3, right? So when we're talking about what percentage decay is this, it'd be 33.3 repeating percent.
Yes.
Decay.
No. Yes. Yes.
Much less than 1. Got to watch those mute button, people. If you unmute, you got to remute. Okay. Horizontal asymptote wise, we're looking at the k value. What is the k value of g of x? What is the k value of g of x?
-4.
Good. -4. So that would be our horizontal asymptote. Y equals -4. All right. Everybody take a second, try h of x, identify the base, identify the k value, tell me whether it's growth or decay. All right, take a second, try that out.
Mr. Wills?
Yeah.
So when it's greater than 1, it's exponential growth, and when it's less, it's exponential decay.
Yes.
What is it when it's like equal to 1?
It will never be equal to 1. B is not allowed to equal 1.
Oh, okay, cool.
Yep. Okay, so hopefully we have identified that the base of h of x is 2. So since 2 is greater than 1, this is an example of exponential growth. If we're looking at the percentage, 2 is greater than 1 by exactly 1 unit being a 100% growth rate. And our asymptote there is positive 1. So we have y equals plus 1 for the horizontal asymptote. Okay. Go ahead and try the next one. We are not going to do the last one right now. We'll talk about that some other time. That's not important right now. Okay, so we're only going to look at this fourth one here for what we need to look at right now. No, never mind. We'll go ahead and look at it. It's easy. We'll look at it anyway. Okay, try those last two. Find the base, identify them as growth or decay, and then we'll talk about the asymptotes. Okay, on k of x, what is the base? Anyone? On k of x, what is the b value? What is the base?
1/2.
Good, 1/2.
-3. Wow, 1/2.
And 1/2 is the number being raised to the power, so that is our base. Okay, and since that number is less than 1, because it's between 0 and 1, that makes this an example of exponential decay. 1/2 is exactly 1/2 of a unit less than 1, which makes this a 50% decay because 1/2 as a percentage is 50%. Okay, remember it's how much below 1 it is, though. It's not, that's a coincidence that it's the same exact fraction. As for the asymptote, that is where the -3 comes in, because even though it's not written on the end, that is the k value. So y equals -3 would be your horizontal asymptote. Now, for the last one, there's a lot in there to digest, a lot of information there that could be throwing you off. First of all, the base is pi over 3. Pi, remember, is approximately 3.14. So when we divide pi by 3, is that greater than 1 or less than 1? Anyone? Is pi over 3 greater than 1 or less than 1?
Greater.
Very good. It is just barely greater than 1. Okay, which makes this an example of exponential growth. We're not going to worry about the percentage there because pi is one of those numbers that never ends. And we're going to look at the asymptote. What is the k value for that last function? What is that k value? It's not 1/4. 1/4 is the a. What is the k value?
0.
0. Good. There is no k value. So the k value would be 0. Okay, there's no k. So k is 0. Okay, so that does it for that section. I'm going to grab my picture here while you guys finish writing it down. Drop that in here real quick. We'll go back out here to where we need to be. Does anybody need more time before we advance to the application section? Okay. We're good to go? Speak now or forever be annoyed. Hey, Colton made it. Should probably update my attendance again. Okay, here we go. So the major application of exponential functions is found here in the compound interest formula. Okay, the compound interest formula is found on page 162 in your pre-calculus textbooks, which you were supposed to have taken home, but that's okay. I'll write it down anyway. It's right there. A equals P times the quantity 1 plus R over N to the NT power. Okay, so there's a lot of stuff in there. Let's talk about what all these things are. A is the balance, the ending balance of the account. P is the principal. Which is the starting balance in your account. However much amount is in your account, that's the principal. R is your annual interest rate. And again, that is as a decimal, not a percent. N is the number of times per year compounded. And that will be a word. And then T is time in years. Now for N, there are a number of different words that can be used. You probably won't see annually, but that would be N equals 1. Semi-annually would be N equals 2. Quarterly would be 4 times a year, or N equals 4. Monthly, well, there are 12 months in a year. Let's see, what else could come up? I don't think we're very likely to see any of those. We could have daily. There are only, for this type of problem, 360 days in a year. So if I see daily, N equals 360. Okay? So that's the compound interest formula. We are going to be using that here in the rest of our examples as we finish out. I'm going to grab a picture of this real quick and throw it into our notes there, and then we will continue to the examples.
Mr. Wills, how many chapters of pre-calculus are there?
Plenty. More than we can cover in a semester, that's for sure.
So are we going to try and get through chapter 3 by the time?
We're going to do as much of it as we can, Tyler.
Okay.
That's all I know for now.
Okay, thanks.
Is Pat's working on chapter 3?
Yes, started today. Okay, so let's move down the page here. Let's do some examples. Again, we've got our equation. I'll rewrite that because it's not going to be on the page here. Okay, remember that we're using the compound interest formula, which is A equals P times 1 plus R divided by N to the NT power. So Mark invests $1,000 in an account with a 6.5% interest rate. What would his balance be after 20 years if he makes no other deposits and his interest is compounded? Should be interest, not interested. Should be interest, if interest is compounded. So let's talk about what we've got. First of all, the principal balance. How much money is he putting into this account? What is his starting balance? What is P? What is the initial amount in the account?
$1,000.
$1,000, perfect. Okay, that's the P value. The principal is $1,000. Interest rate, 6.5%. How do we write 6.5% as a decimal? How do we convert a percentage to a decimal?
Divide by 100.
Divide by 100. Very good. So 6.5% would be, as a decimal, 0.065. We move that decimal place 2 places to the left. So our interest rate is 0.065. The other thing that we know here is the time. T is 20 years. Okay? So we're going to do this 3 different times with 3 different n values so you can see how this works. If we're looking at semi-annually, that means twice per year, so n equals 2. So A would equal the principal, 1,000, times 1 plus 0.065 divided by 2 to the 2 times 20th power. Now that should be something we can type directly into our fancy schmancy calculators, exactly like it is written. So 1,000, open parentheses, 1 plus 0.065 divided by 2, close. Then hit the caret button, which is the button directly above the division symbol. That'll give you up to an exponent. And as the exponent, 2 times 20. Hit enter. You should get this number. $3,594.201434. Okay. Now this is dollars and cents. So what should we round that to? This is a money amount. Where should we round that off? Okay, we should round it off here at the cents, which is 2 places past the decimal. That 1 tells us to round the 0 down or keep the 0. So A would be $3,594.20. Okay, let's look at monthly. If we do monthly, all that changes is that n equals 12 instead of 2. So when we go to plug this in, we would say A equals 1,000 times 1 plus 0.065 divided by 12 to the 12 times 20th power. Again, we're going to feed that directly into our calculator. Type it in exactly as it reads. Okay, so we're typing that in. 1,000, open parentheses, 1 plus 0.065 divided by 12. Close parentheses, caret 12 times 20. We should get 3,656.446702. Again, this is dollars and cents, so we should round that after the 4. The 6 tells us to round that 4 up, which means our answer should be $3,656.45. One more time here with daily. If we do daily, well, that makes n into 360. You're not going to find very many banks that give you compounded daily. There's a reason why you're going to see shortly. So again, that would be 1,000 times 1 plus 0.065 divided by 360 to the 360 times 20th power. So 1,000, open parentheses, 1 plus 0.065 divided by 360, caret 360 times 20. That would be 3,668. Again, we're going to round that number off at the cents. That 6 would tell us to round our answer up. So we would have $3,668.87. Again, the more times that it is compounded per year, the more interest you're earning. You will not find very many banks that offer anything more than compounded monthly, because again, any increase in the number of times they compound is more money they have to give you, which they're never fond of doing. Okay, so there we go. That is how we find the future balance. So any questions on that portion of the notes so far? If so, just unmute or drop it in the chat. Okay, any questions so far? Okay. So we're going to have to stop there for today. We'll cover the rest of these notes quickly Friday, and then we'll go on from there to talk about the other part of 3.1, which we still need to talk about. Okay, so we're going to stop there for today. Again, your assignment is on Delta Math. So one thing you are going to need to do here in these last 2 minutes is go make sure that you can log in to deltamath.com. Again, in theory, we've used it this year. So everybody has logged into it this year. It should be your school email and then whatever password you were using. If you can't remember your password, I can reset it. So just send me an email if you don't remember your password, if you cannot get in, and I will help you by resetting your password. Your username should be your school email. Okay, so I want everybody to go check and make sure they can get into Delta Math now. And that's it for today. You'll have the Delta Math assignment that's due on Friday. Okay, you don't need to stay on the Google Meet while you do that. You can go, but do go now and check to make sure that you can get into your Delta Math. Because if you can't, we need to set the password today. We need to get that handled, okay? So go check, make sure that you can get into your Delta Math account. Again, your username should be your school email. Your password is whatever you had it set to. Go make sure you can log in. Homework's due Friday. Homework is due Friday.
See you, Mr. Wills.
Bye.